Hey everyone. By the way, that was Devo. I saw them live in concert at the Warfield the fall before last, and they're still fantastic performers. Flower pot hats and all. This is too loud. All right. So we're going to pick up where we left off last time with linear time sorting algorithms. I talked about bucket sort last time. Today I'm going to start with another sort that's very, very similar to bucket sort. You apply it in almost the same situations. It's called counting sort. There are a couple of versions of counting sort. Both versions, like bucket sort, work best when the keys are in a very narrow range. So you have a small range of keys, like maybe you know all your keys are between 0 and 1,000, and the number of keys that you're sorting is roughly at least as big or much bigger than the number of different possible keys. So when you do that, you can choose between bucket sort or counting sort. There are two versions of counting sort I want to teach you. I'm going to start with the very easy version. The very easy version happens when we want to sort keys and there is no associated information with those keys. So usually you're sorting something like a database record where maybe you have a big record to sort based on last name. Something going on? Everyone's got their hands up. Uh-oh. That is weird. I have no idea why it's doing that or what to do about it, but will this make a difference? That is weird. I don't know why it's doing that. That's brand new. Well, this is a major annoyance. So we're in a situation where we're sorting a bunch of keys that have no associated values. And so, for instance, maybe I'm sorting a list of numbers, but there's no other information, a source associated with those numbers. So you can, if you someone just gives you a list of numbers in a small range, you can use the sort I'm about to tell you to sort them, but it just sorts the numbers. You couldn't use it, for instance, to sort the edges in Kruskal's algorithm, because what I'm about to tell you won't move the edges along with their weights. Now, counting sort is a lot like bucket sort, but there are no queues. Instead, we keep a count of how many copies of each key there are. And that's pretty much what we do. And that's going to make this pretty much, in some ways, the simplest sort algorithm we look at this semester. Because here's how it works. Suppose that this is our input. Suppose I have this list of numbers, and I want to sort them. Well, I start by noticing that all these numbers are in the range between 0 and 7. So I can sort them with a count array that goes from 0 to 7. Now I'm just going to go through the list from left to right and count up how many times I see each number. So the first number is 6, so I count 1 in the 6 box. The next number is 7, 1 in the 7 box. A 3, put it in the 3 box. A 0, put that in the 0 box. A 3, I'm going to use the sort of prisoner's counting method where you just give 1 stroke for each one, so these numbers are in unary. Next, there's a 1, so we count 1 in the 1 box. There's a 5, we count 1 in the 5 box. A 0, now we have 2 in the 0 box. 3, now we have 3 in the 3 box. And finally a 7, so now we have 2 in the 7 box. So what this means, what I've just written, is that we have counted 2 zeros and 1 1 and no 2s and 3 3s, no 4s, 1 5, 1 6, 2 7s. So the final step is I just go ahead and I write those numbers out. I say, well, we have 2 zeros, we have 1 1, we have no 2s, we have 3 3s, we have no 4s, 1 5, 1 6, and 2 7s. I can't draw a 6, but... So that's it. That's the whole algorithm for the basic version of counting sort. Again, pretty much the simplest sorting algorithm you can imagine. Any questions about it? All right, now I'm going to complexify it a bit. We're going to do version 2 of counting sort. But now I want to go back to being able to sort database records or edges in Kruskal's algorithm or other information that involves not just a key but a bunch of stuff that has to move around with the key. So this will be a more complicated version of counting sort. Based on the same idea, but we need some extra ideas on how we're going to get the input items to move to the correct spaces in the output array. So again, remember when I say complete items, I mean that there is a key plus an associated value, like a database record, that goes along with that key. And so when you sort the phone book, you're sorting on the key, the last names, but you're also sorting phone numbers. I'm going to give my input array a name. I'm going to call it X. And the idea is that, for now, let's think of this as an array of objects. There's more than one way to do it, but this is one way to do it. Have an array of objects, and each of those objects contains a key, but also contains other information, the whole database record. So, whoops. So now our input array X is going to look like this. I am still sorting the same numbers as I was sorting before. It's just that now inside these boxes I can put other information in addition to the numbers that I'm actually sorting. We're going to start this version of counting sort exactly the same way we did the basic version of counting sort, which is we're going to count the keys. This time I'm going to give you pseudocode, well, actually, no, I'm going to give you actual Java code so that you can see how counting sort would work when we're doing the hard part, which is moving all this stuff around. So here are our 3 lines of code that will count the keys for us. All right, so we walk through all the keys in the array from left to right, and for each one, we look up in the array what is the key in that object. Then we use that key as an index into the counts array that I showed you earlier, and once we find the right count, we increment that counter by 1. The next step, the hard part, is now that I know how many copies there are of each key, I want to take each object in the input array, x, and move it into a new array, an output array, so that every object is in its correct place in that output array, and all your database records are sorted. So to do that, I'm going to do that in 2 steps. The first step is something called a scan. All right, so what a scan does is it walks across the array and it does a sum, an increasing sum as it goes of the items in the cell. And the idea is when I first create the counts array, it tells me the count of key I for each I. But what I really want is something slightly different. I want a count of all the keys that are less than I for each I. The reason I want that is that's going to tell me the index to which I should store the keys I in the output array. So the way you do a scan is you start from the left end of the array and move towards the right, and you increment things as you go. And let me draw what we're trying to achieve first. The counts array after we do the scan will be a bunch of sums. These are sums of all the numbers in the original array. So, for instance, the number 8 here is the sum of all of the entries that were to the left of this 8 in the counts array before I did the scan. And this 6 is the sum of the numbers that were in these boxes before I did the scan, and so on. And as it happens, the first number is always 0 because there are no keys less than 0. Question? Okay. So again, the purpose of this array is to tell us where in the output array we want to put keys. So this tells us that we want to put the keys that are 0 starting at position 0 in the output array. And we'll put the keys 3 starting at position 3 in the output array. And we'll put the key 6 starting at position 7 in the output array. So here is the code that computes that scan. And so this code comes right after the counting code I just showed you. So this code keeps a running total in a variable total as it goes from left to right across the counts array and adds up the numbers. And that's how you get that array of numbers up top. So again, this tells us where to put things in the output array, which I'm going to call Y. Now that we know these indices, the last thing we want to do is walk through the array X, the input array that has all the items in it, from left to right, and move each item in the input array to the appropriate place in the output array. And this counts array tells us where the appropriate place is. So here is the last piece of code that puts everything in the proper position. So we walk through the input array, X, from left to right. And the next line of code is maybe a little mind-boggling. So we need to move this item xi to its proper place in the output array. So to find the proper place, we need to look up the key of xi, and then we look up in the counts array what is the index we should send that item to in the y array. After we do that, we also need to increment the count array in that same location. And the reason why we have to do that is so that if we have another item with the same key, we don't want it to overwrite the previous item with the same key. We want it to go next to the item with the same key. And that's all the code. So that's all the code for counting sort. Let's come back to what does this little snippet of code do? Well, again, here's the counts array after we do the scan. And the output array, which I'm going to call y, goes right here. Okay, I'm going to go through the input array, again, from left to right. The first input number was a 6. So I look in the box in the counts array called 6, and what's in that box is a 7. The 7 means I want to put that 6 in index 7 in the output array. So that 7, you can think of it as pointing down there. And that means this is where I want to write the 6 into the output array. And then we go on to the next key in the input list, which is a 7. And we look at the 7 box, and that tells us that the 7 should go in index 8. The other thing is, every time we do this, though, we also increment the count. So when we did the 7, or index 7, we increment that so that it's an 8. And when we did the 8, we increment that so it's a 9. And the reason why we do that is the next time I find a 7 in the input list, I don't want to put it here. This space is already taken. I want to put the next 7 here next to the previous 7. So I increment that 8 to 9. That tells me next time I have a 7, I want to put it in this slot, not in this slot. And continuing our way through the list, our next number is a 3. So we look in location 3, and it says put the 3 at index 3. So that's what we do. And then we increment that 3 to 4 so that the next 3 that comes along will go here. Now the next key is a 0, so we know put that in the 0 slot. And that gets incremented to 1. The next key is another 3, so this time the 3 is going to go in the 4 slot. And the 4 gets incremented to 5. The next key is a 1. So we look in the 1 box, and that says, well, no, it doesn't say that. It says, put it at index 2. And so the 1 goes at index 2. The next key is a 5, so that this says, put the 5 at index 6. So that's what we do. The next key is a 0. This says, put the 0 at index 1. So we put the 0 at index 1, and we increment that. The next key is a 3. So once again, we look in the 3 box, and now it says 5. So we put a 3 at index 5, and we increment the 3 count. The last key is a 7. This box says put the 7 in index 9, so that's what we do. Increment, and now we are finished sorting. Questions about that? Yes?
This algorithm will require you to find the largest element in the list. Is there any quick way to do that besides cycling through the entirety of the list or array or what have you to find it? Is there any quicker way to do that than just go through the entirety of it?
So, right, in this algorithm you do need to go through if you want to know how many buckets you need to use or how many counts you need to use, then both counting sort and bucket sort do require you to somehow know what the maximum and minimum keys might be. And generally, if you don't know anything about the keys at all, then yes, the only way to do that is you have to scan through the whole input and look at what the minimum and maximum keys are. There are a lot of situations that come up in the real world where you do know what the minimum and maximum keys are for other reasons. And in fact, the very next sort I show you, Radix sort, will be one such situation where that is true. So you'll see why in a few minutes. Question in the back. So when you say the 7 box and the 8 box, I'm not sure whether you mean the top or the middle 7 box and 8 box. So. So in other words, you're asking, when I say increment this number here, do I also have to increment these numbers here? Okay. And the answer is no, I don't. When I am incrementing this key here, the reason I'm doing that is it tells me, okay, I have now filled in this space here. I don't want to fill in that space again. I want to make sure that next time I see a 3, I fill in this space instead. But that's not going to affect different keys like 5s because I know that the first, say, 5 is supposed to go in this box here. And the fact that I happen to find one of the 3s first doesn't change the fact that when I do find a 5, it needs to go in that box. Does that answer your question? Okay. Other questions? Yes? Well, this happens in n plus q time, which may or may not be linear depending on how you count it. So n being the number of items you're sorting, q being the number of queues, or the number of counts, the number of buckets, however you want to put it, the number of possible different keys that might appear in your input list. And so it's linear in those two things added together, which you may or may not consider linear depending on the circumstances. O of Qn? I don't. It's definitely possible to have repeated items. But yes, so it's possible for n to be bigger than q when you have lots of repeated items. Even if you don't have lots of repeated items, it's possible that n is in big O of q. But there are certainly circumstances where n is very small compared to q, and then this is not a good sort to use. Right, q is possible items, exactly. So let me write this down for y'all. So we're talking about running times here. And bucket sort and counting sort are both essentially the same in their behavior with respect to running times. They both take big O of q plus n time. And in fact, theta of q plus n time, and that's both the worst case and the best case time, because it takes q time to initialize the counts array and to do the scan. It takes n time to go through all the items, increment their counts, go through all the items a second time, and put them into the correct spot in the output array. So if q, which is the number of possible items, the range of our items, if that number is in big O of n, then we're very happy. Because they take time proportional to the number of items we're sorting. But again, there are many situations in which that's not true, where the range of possible items is from 0 to 10 quadrillion, and you're only sorting 1,000 items. And so this is not the sort for that situation, though we will see a sort in a minute that is for that situation. Before I go on to that, though, I want to say, when would you use bucket sort? When would you use counting sort? The most obvious reason to choose one over the other is depending on what kind of data structure you're sorting. So if you're sorting an array, then counting sort is faster. And even though the code is a little non-intuitive, it's probably simpler overall. But if you're sorting a linked list, well, bucket sort is the natural sort for sorting a linked list. And the reason for that is bucket sort uses linked lists. It uses chains of list nodes. If you've already got list nodes, then it's natural to just put those list nodes into buckets without messing with them and sort them in the buckets with bucket sort. So any other questions about that? All right, so the next question we want to address is, what do we do if the number of possible items is in a very big range, like from 0 to 10 trillion, and the number of actual items we want to sort is much smaller. These algorithms, bucket sort and counting sort, aren't suitable for that situation, but there's a way to fix them so that they are. And the algorithm that does that is called Radix sort. The word radix means the base of a number. So when we talk about, say, base 12 numbers, you can also call them radix 12 numbers. And radix sort is based on the idea of sorting numbers digit by digit in a base or a radix of your choice. So for instance, let's suppose that I want to sort 1,000 items. And the range of those possible items is, say, from 0 to 99,999,999. Well, you could sort them with bucket sort, and if you do that, you'll have to create 100 million buckets. And you'll spend so much time initializing and concatenating empty buckets that you'll wish you'd use selection sort instead. So bucket sort's just not suitable for this situation, but we can fix it so it is. What we're going to do is we're going to say no to 100 million buckets. That's too many buckets. That takes too much time. But we will provide 10 buckets. Well, that's not enough buckets, so we're going to sort on the first digit only. So, by the way, I'm going to assume that we've written out all numbers in 8-digit form. So if there's any number that's less than 8 digits, we put zeros in front of it to pad it out to 8 digits. So any number less than 10 million is said to have a first digit of 0 for the purposes of sorting. So now what I'm going to do is I'm just going to do a normal bucket sort or counting sort, your choice. They both work. But I'm only going to sort on the first digit. I'm going to ignore all the other digits of the number. So if the first digit is a 3, if your number is something like 395088883, then it goes in the 3 bucket. And within each bucket, the numbers are not necessarily sorted in any particular order. But we'll fix that later. And so the 0 bucket gets anything less than 10 million. Again, pretend that first digit is a 0. All right, so you take 1,000 numbers and you keep doing this until you put all the 1,000 numbers in buckets. So once you reach this point, the numbers are partly sorted. They're not fully sorted, but you've divided it into 10 different queues that are all in the right order. And now you want to get each queue sorted. There are 2 ways you could go about doing this. One is you could recursively bucket sort each queue on the second digit. And then when you're done sorting all the numbers in that first queue on the second digit, now you take each of the 10 queues you get out of that and you sort each of those on the third digit. And you keep doing this recursively. You break up your numbers into smaller and smaller queues, and you sort them on each digit in turn until you've sorted all the numbers on all the digits. Turns out that this is not the ideal thing to do, though. The reason why is you're taking this big queue and you're breaking up into smaller and smaller queues, and you're calling this recursive method on smaller and smaller queues, and you wind up calling this recursive method many, many times. There is something you can do that is simpler and a little bit faster, but it's less intuitive. So this is the clever idea. Behind how a radix sort is really done. We're not going to divide the pile of numbers up into smaller and smaller queues and sort those all separately. We're going to keep all the numbers together in one big pile throughout the sort. We're not going to keep dividing it into smaller and smaller pieces. But, here's the counterintuitive part, we're going to make up for that by sorting on the last digit first, the least significant digit. Instead of sorting on the first digit first, we sort on the last digit first, then the second last, then the third last, then the fourth last, and so on up to the first digit. We sort on the first digit last. Now, this works, and the reason it works is because counting sort and bucket sort are stable. So what that means is that suppose we've sorted on the last digit, and when you sort on the last digit, the number 5555552 will be placed before the number 5555558 in the sorted list, because we're just sorting on the last digit, and no matter what happens, that number has to come before that number after we sort on the last digit. Once we do that, we're going to sort on all the other digits. We're going to sort on the second smallest digit, the third smallest digit, and so on up to the most significant digit. But because bucket sort is stable, this key will always stay in front of this key in the sorted list. They will never exchange sides again. So consider an example with 3-digit numbers, which is hard with such a narrow screen, but the idea is, suppose we first sort on the ones digit, and we get this set of numbers. Numbers that end with 1, numbers that end with 2, numbers that end with 5. Numbers that end with 7, end with 8, and with 9. So here I've got 3-digit numbers. They were given to me in some totally random order. I sorted them on the ones digit, and you can see they are sorted 1, 2, 5, 7, 8, 9, but only on the last digit. Having done that, now I will sort on the middle digit, the tens digit. And this seems to rearrange everything. So now, first come numbers with 0 in the middle, then come numbers with 2 in the middle. But one thing I want you to notice is that in the first round, when we were sorting on the ones digit, the number 771 got placed before the number 777. They weren't placed next to each other, but 771 came before 777. Then when I sort on the tens digit, it's going to stay that way because bucket sort and counting sort are stable. So the 771 is still in front of the 777 after I sort on the middle digit. The middle digit is 7 for both those numbers. You could have put it in either order if you weren't using a stable sort, but the stable sort keeps them in the correct order. And then finally, when you sort on the hundreds digit, everything magically comes out in the right order. So first come the numbers that begin with 0, then the numbers that begin with 4, then the numbers that begin with 7. So at this point, everything's sorted. Let's again look at a pair of numbers. 771 and 721 were initially in the wrong order. But after we sorted them on the middle digit, they wound up being in the correct order. And then when we sorted them on the first digit, they both have the same first digit, but the sort is stable, so they're still in the correct order. Any questions about that? Yeah.
Do you have duplicates in your input? So like 777 and 777?
Yeah.
In that case, how would it still keep that stable?
Well, if you have two input keys that are both 777, then every one of these sorting steps is going to keep them in the same order they were in the input list. They'll never swap places in the list. They'll move around relative to the other keys, but they'll never swap places with each other. So things with the same key stay in the same order they were in the input list. Yes? How much time does this take? That's the complicated part, and I'll go over that in a minute. Just want to make sure everyone understands the algorithm first. Other questions? All right. So I want to make a few points about this. The first point is that I don't necessarily have to just use 10 buckets. I can pick any number of buckets I want. So let's go back to the original situation I was talking about where I want to sort 1,000 items in the range from 0 to just under 100 million. So 8-digit numbers, there's 1,000 of them, I want to sort them. Instead of sorting them 1 digit at a time, I could sort them 2 digits at a time. So if we sort 2 digits at a time, another way to think of that is imagine you don't express the numbers as base 10 numbers. Imagine you express them as base 100 numbers. So instead of 8 digits from 0 to 9, now we have 4 digits from 0 to 99. In other words, we think of it as a base 100 number, or we set our radix, the number of buckets, to 100. Or we could sort on 3 digits at a time, which is equivalent to sorting with base 1,000 numbers. So I set the radix to 1,000, which means I set the number of buckets I'm using in the bucket sort to 1,000. And for that matter, we don't have to restrict ourselves to powers of 10 because computers don't really like powers of 10 anyway. Computers are faster and act much more naturally with bits. So they really like powers of 2. They like things like base 256 numbers. So if you sort your keys 1 byte at a time, meaning 8 bits at a time, meaning you're using a radix of 256, then that means you create 256 buckets for your bucket sort, and you use that to sort. And it turns out it's much faster for computers to extract 1 byte at a time from a number than it is for a computer to extract a base 10 digit at a time from a number. Because you can get the base 256 bytes just by doing bit operations, which you'll learn about in CS61C. So again, I want to remind you that this number Q is 2 different things. It is the number of buckets that we use in the bucket sort. Or if you're doing counting sort, it is the number of different counters you have. But it is also the radix of the digit we use as a sort key. And so when you have a really long number with a really big range, you break it down into a bunch of short digits with a really small range so that you don't have too many buckets. So now let me come to the question I was asked, what is the running time of radix sort? To figure that out, to figure out time, first we have to ask the questions, how many passes do we have to perform of bucket sort or of counting sort in order to completely sort a bunch of keys? And that depends on how long the keys are and how many buckets we're willing to use. So here's a slightly mind-blowing idea. Each pass that we do, if we have Q buckets, each pass is going to inspect log Q, that's the base 2 logarithm, bits of each key. So if I use 256 buckets, I am examining 8 bits of each key at a time. And if I'm using 1,000 buckets, well, yes, you can examine a fractional number of bits at a time. In this case, it would be just slightly less than 10 bits if you used 1,000 buckets. And yes, it actually does make sense to talk about a fractional bit and divide numbers into fractional bits, because that's essentially what you do when you use a number of buckets that's not a power of 2. So how long are the keys? Well, let's just suppose that all the keys we want to sort are represented in B bits, where B is some constant. And this is usually true in practice. Usually you're sorting things like ints. Ints are 32 bits. That's a constant. So that means that the number of passes of bucket sort you have to do is equal to the number of bits divided by the number of those bits that you can inspect in one pass of bucket sort. Now, you can't do a fractional pass. You can have fractional bits, but you cannot do a fractional pass of radix sort. So you have to take the ceiling of this, which means we round it up to an integer, because you can only do an integer number of passes of bucket sort. So that's the number of passes, and then the running time of radix sort is in big O of, well, how long does one pass of bucket sort take? It takes n plus q time. And now you multiply it by the number of passes of bucket sort we have to do, which is this ceiling of b over log of q. And that is the running time of radix sort. All right, so I know that looks a bit yucky, but it's also really interesting for a reason. Q is a number that we get to pick. We decide how many Qs we're going to use. If you pick Q to be big, this expression on the left is big, but the one on the right is small. If you pick Q to be small, then the reverse is true. And so you might ask, should we make Q small so that this part stays small? Or should we make Q big so that this fraction stays small? Well, it turns out that if you were to actually graph it, if you were to actually graph the running time as a function of the number of Qs, you get a U-shaped curve, and you want to find a nice spot in the middle. And, well, so we get to choose Q again. How do we do it? Well, we decide that we want Q to be not bigger than big O of n, so that each pass of bucket sort takes truly linear time. But we want Q to be large enough to make the number of passes small. And so generally you get a nice trade-off when you choose Q to be approximately, say, some constant factor times n. And when you do that, then the running time is in big O of that, which is a little bit simpler. And the other thing to notice is that b is usually a constant. So if b is usually a constant, then the second term just reduces to linear time. So for instance, suppose we're sorting ints. Then b is a constant, and therefore you get just big O of n time. Radix sort takes linear time if you're sorting something with just a constant number of bits. Finally, I just mentioned, in practice, I recommend that you always also choose a power of 2, because computers like that. So I would suggest usually you take n and you round it down. Remember, n is the number of items we're sorting. You round it down to the next power of 2, the next smaller power of 2, and you use that as the number of buckets in your bucket sort, and then your radix sort takes linear time. And I'll see you all on Wednesday.